An electrochemical cell utilizes a spontaneous oxidation-reduction reaction to generate electrical energy. Hi, this is Mr. B. In this video, I'll explain how chemical energy is converted to electrical energy in an electrochemical cell. Consider the reaction between zinc metal and copper 2 nitrate to produce zinc nitrate and copper metal. This is a spontaneous oxidation-reduction reaction. To prove this, simply rewrite the chemical equation in its net ionic form, where the spectator ions are excluded. The net ionic equation for this chemical reaction is written as follows, where solid zinc reacts with aqueous copper 2 plus cation to produce aqueous zinc 2 plus cation and copper metal. Now the question is, well, okay, how do we know the forward reaction is indeed spontaneous when the reverse reaction seems to be entirely possible? The reverse reaction will be a non-spontaneous process. To prove this, let's consult a table of reduction and oxidation potentials. When evaluating the oxidation and reduction potentials for the elements and ions involved in this reaction, the spontaneous reaction becomes apparent. Consider the forward process where zinc undergoes oxidation to produce zinc 2 plus cation and 2 electrons. The oxidation potential for zinc metal is actually a positive 0.76 volts, where a positive value means that the process is favorable. From a table of reduction potentials, the reduction potential for copper 2 plus ion to produce copper metal is a positive 0.34 volts. Once again, the positive value indicates that the process is favorable. Now let's consider the reverse, where copper metal actually undergoes oxidation. The oxidation potential for copper metal to produce copper 2 plus ion is actually a negative 0.34 volts. Exactly the opposite of the reduction potential. The potential for zinc 2 plus cation to undergo a reduction to produce zinc metal is exactly the opposite of its oxidation potential. The reduction potential for zinc 2 plus cation is actually a negative 0.76 volts. From this data, it becomes apparent that reaction A will be spontaneous, since both the oxidation and reduction potentials have positive values. And the reverse reaction, represented by equation B, will be non-spontaneous, since both values are negative. Okay, now let's relate these processes to a functional electrochemical cell. Remember, zinc will undergo oxidation and copper 2 plus ion will undergo reduction. An electrochemical cell consists of two half cells, two electrodes connected by wire through a device, and a salt bridge. In this example, the electrodes will consist of the metal zinc and the metal copper, where the solutions will be consistent with the chemical equation. In the cell on the right, the solution will be zinc nitrate. On the cell on the left, the solution will be copper 2 nitrate. The two cells are connected by a U-tube containing an aqueous salt. In this particular case, the aqueous salt will be sodium nitrate. And of course, the electrodes are connected by wire through a voltmeter. Notice that in this case, this circuit is open, Therefore, the reading on the voltmeter will be 0.00. After the circuit is closed, the following processes will occur simultaneously, where the zinc electrode will undergo oxidation, forming zinc 2+ cation and 2 electrons, which will travel through the wire. Since the zinc electrode is undergoing oxidation, this electrode is known as the anode, and because the electrons are being generated at that electrode, the charge is negative. The line notation for this process is written as follows, where zinc metal undergoes oxidation to produce zinc 2+ cation, where the vertical line represents the phase border. In the cell containing copper, copper 2+ ion will undergo reduction. The electrons released by the zinc metal as it undergoes oxidation will now be utilized by the copper 2+ ion in solution. The copper 2+ ion will be attracted to the electrons that were generated at the anode. At this point, the copper 2+ cation undergoes reduction, where the copper 2+ cation will form copper metal. Since reduction occurs at this electrode is called the cathode and will have a positive charge. As the copper 2+ ion undergoes reduction, it will plate onto the electrode. Therefore, during this process, the cathode will actually increase in size. Line notation for the cell containing the cathode will be written as follows, where copper 2+ cation undergoes reduction to produce copper metal, where the vertical line represents the phase border. As the anode undergoes oxidation, it will essentially dissolve. Therefore, during this process, the anode will actually decrease in size. So, as the process continues, the cathode increases in size and the anode decreases in size. During the oxidation process, zinc 2+ cation will be produced. However, the production of zinc 2+ cation will cause a charge imbalance in the half cell containing the anode. To neutralize that charge imbalance and maintain an overall zero charge, the nitrate ion from the salt bridge will migrate into the cell containing the anode. As the negative nitrate ion migrates into the cell, the nitrate will essentially neutralize the excess positive charge. In the cell containing the cathode, copper 2+ ion is continually being reduced. This reduction removes copper 2+ cation from the solution, which leaves behind the negative nitrate anion. This will cause a charge imbalance in the half cell containing the cathode. However, this charge imbalance will be negative. To cancel a negative charge, the sodium cation will migrate from the salt bridge and essentially neutralize the excess negative charge. The function of the salt bridge is to allow the migration of ions from one half cell to the other half cell. During this process, the electrons will flow from the anode through the device to the cathode. Under standard conditions, the reading on the voltmeter will be 1.10 volts, where the reading indicates the sum of the oxidation potential and the reduction potential. The standard cell potential is equal to the standard oxidation potential plus the standard reduction potential, where the standard oxidation potential was a positive 0.76 volts and the standard reduction potential was a positive 0.34 volts. In a standard electrochemical cells, the solutions will be of the following concentrations, where the cell containing the copper 2 nitrate will have a concentration of 1 mole of copper 2 nitrate, and the cell containing the aqueous zinc nitrate will have a concentration of 1 molar zinc nitrate, and the salt bridge, which contains an aqueous solution of sodium nitrate, the concentration of this solution will also be 1 mole.